Finally, we're going to look at this reaction stoichiometry activity. This was a separate handout. It's still a gold handout. You should have received it in class. So we're looking at the following balanced chemical equation where 2 moles of N2H4 react with 1 mole of N2O4 to form 3 moles of N2 and 4 moles of H2O. As we go throughout these problems, we're going to need our molar masses. So here I've calculated the molar mass of N2H4. Remember that the molar mass is just based on the chemical formula. The molar mass does not take into account this coefficient. The molar mass of N2O4 is 92.02, and for N2 we've got 28.02, and for water we have 18.02. Question number 1 says, calculate the moles of N2 that will form if 0.755 moles of N2H4 react with excess N2O4. So in this case, I've already given you moles, 0.755 moles of N2H4. We don't care about the N2O4 in this problem, so we know that 2 moles of N2H4 relate to 3 moles of N2. So because I've already given you moles in this problem, we're going to start right with this 0.755 moles of N2H4. We're going to get our conversion factor such that our moles of N2H4 cancel in the denominator. Our moles of N2 are what we will be left with in the numerator, and we have our 3:2 mole ratio, again coming right from the coefficients of the N2H4 or the N2 right here. The final answer when you do the calculation is 1.13 moles of N2. In the second question, it says calculate the mass in grams of water that will form if 24.3 grams of N2O4 react with excess N2H4. So in this case, be very careful with your chemical formulas. In this problem, we have excess N2H4, so this component will not matter. It's a reaction with N2O4, so this is the component that we're focused on, and we need to relate it to water. So what we see in the balanced chemical equation is that 1 mole of N2O4 relates to 4 moles of water. So in order to relate these two components, we must be in units of moles. So the first thing I'm going to do is take my 24.3 grams of N2O4, using its molar mass of 92.02, I'm going to convert to moles. If you do the calculation, you should get 0.264 moles of N2O4. Once I have moles of N2O4, I can convert to moles of any other component, and in this case I'm going to go to water. So now I have my conversion factor that's going to be my 4 moles of water divided by my 1 mole of N2O4. My units of moles of N2O4 will cancel. I'll be left with moles of water, and if you do the calculation, you should get 1.06 moles of water. Finally, the question has asked us to go specifically to grams, so we need the molar mass of water. Here we have 4 moles of water from our conversion factor, but remember the relationship that we need here is the molar mass of 1 mole of water. So that's going to be 1 mole of water in the denominator, 18.02 grams in the numerator. And when you do the calculation, you should get 19.0 grams of water. Now as we look at number 3, we're going to calculate the mass in grams of water that will form if 24.3 grams of N2H4 reacts with excess N2O4. So again, we don't care about the N2O4 here. We're focused on the relationship between N2H4 and water. So I have 24.3 grams of N2H4. The very first thing I need to do is go to moles so that I can relate it to water through the balanced chemical equation. So I'm going to use my molar mass of 32.05 grams as it relates to 1 mole of N2H4. And when you do the calculation, you should get 0.7582 moles. From there, I have moles of N2H4. I need to relate it to water. If you look back up at the balanced chemical equation, we see that 2 moles of N2H4 relate to 4 moles of water. So when we use that information down here, that means that we're going to have 4 moles of water in the numerator, 2 moles of N2H4 in the denominator. And if you were to do the calculation, you would get 1.516 moles of water. Finally, the question asks us to get to grams of water, so we're going to take the fact that 1 mole of water has a mass of 18.02 grams, and the final calculation that you get here should be 27.3 grams of water. If we go to the back side of your handout, question number 4 says, given the following balanced chemical equation, calculate the mass in kilograms of FeCl2 that will form if 858 grams of FeS react with excess HCl. So here we're looking at the reaction of iron 2 sulfide with hydrochloric acid to form iron 2 chloride, in dihydrogen sulfide gas. In this particular equation, we need to relate specifically my iron 2 sulfide component with my iron 2 chloride component. So we see here that we have a 1-to-1 mole ratio. We're starting with a mass and we need to calculate a mass, so our molar masses will be helpful with this problem. So FeS has a molar mass of 87.92 grams. FeCl2 has a molar mass of 126.75 grams per mole. If I start here with my 85 grams of iron 2 sulfide, I can convert from grams to moles using that molar mass. If you do that calculation, you get 9.76 moles of FeS. From there, we need to relate our two components. Once I have moles of FeS, I can convert to the moles of FeCl2 that I need using my mole ratio, which in this case is a 1-to-1 mole ratio based on the coefficients that you have from this balanced chemical equation. Now the next thing I'm going to do is go to grams. 1 mole of FeCl2 has a mass of 126.75 grams, and if you do that calculation, you should get 1,240 grams. Finally, because this reaction has been run on such a large scale, you've been asked to calculate your final mass in units of kilograms. We know from the very beginning of the semester that 1 kilogram is equal to 1 times 10 to the third grams, and when you do that conversion from grams to kilograms, the final answer that you get is 1.24 kilograms. If I go down to question number 5, it says, given the following balanced chemical equation, what is the mass in milligrams of Cl2O5, where I give you the molar mass of 150.9 grams, that must react in order to form 59.1 milligrams of ClO2, where I give you the molar mass of 67.45 grams. In this problem, you've been asked to calculate a mass for Cl2O5. Okay? Keep in mind from the balanced chemical equation that that is one of your starting materials. In this problem, we have been given a mass of our product, ClO2, right here. So rather than going from a starting material to a product like we've done in so many examples before, in this case we're going to go in the opposite direction. We're going to go from the mass of a product and calculate the starting material that we need in order to form that particular mass. We still know that for every 2 moles of Cl2O5 that we start with, we'll make 4 moles of ClO2 as our product. But again, in our stoichiometric calculation, we're starting with product information and we need to use it to calculate starting material information. So the first thing I need to do is take this mass in milligrams and convert to grams. 1 milligram is equal to 1 times 10 to the negative 3 grams, and when you do that calculation, you should get 0.0591 grams of ClO2. From there, we can go to moles using our molar mass, and when you do that calculation, you should get 8.76 times 10 to the negative 4th moles of ClO2. Once we have moles of ClO2 based on the units here in the numerator, we can relate our two components through the balanced chemical equation. So that means that we're going to need moles of ClO2 here in the denominator. We need to convert to moles of Cl2O5 right here in the numerator. And so when we do that, we see that Cl2O5 has a coefficient of 2, ClO2 has a coefficient of 4, so that's going to give me a 2/4 conversion factor for this problem. When you do that calculation, you should get 4.38 times 10 to the negative 4th moles of Cl2O5. From there, now that we have moles of the component that we have been asked about, now we need to go from moles to grams, and finally from grams to milligrams, and the answer that you calculate should be 66.1 milligrams of Cl2O5. So remember that stoichiometry allows us to relate moles of any two components in the balanced chemical equation. Often we do calculations starting with information about a starting material in order to learn about the amount of product, but in this question right here we did the reverse. You were given information about a product and asked to do a calculation about a starting material, but our stoichiometric relationships still allow us to do that conversion.